Redox reactions. Redox reactions include two processes, oxidation and reduction. They're both defined in terms of electron transfer. Oxidation is defined as the loss of electrons, and reduction is defined as the gain of electrons. Electrons lost through oxidation are gained through reduction, thus the net amount of electrons remains a constant. And each of reduction and oxidation is a half reaction, and they always come in pairs, and the amount of electrons gained through reduction is equal to the amount of electrons lost through reduction. For example, in this case, the electron from red is given to blue, and also red is a reducing agent and blue is an oxidizing agent. And what this means is that red is itself oxidized, which allows blue to be reduced, and blue is reduced, which allows red to be oxidized. Thus, a reducing agent causes other atoms or substances to be oxidized or to be reduced, and oxidizing agents cause other substances to be oxidized. Here are the rules for determining oxidation states. In order to determine oxidation states, assign those which are easy to determine first from the rules for determining oxidation states. Then use a general data package to determine through elimination the oxidation states of the other atoms in a molecule. Average oxidation state is the average of the oxidation states of the same atom in a compound. For example, in the compound ethene, C2H4, the average oxidation state of the carbon atoms is -2. Although it is usual to have oxidation states that are integers, which is like generally every question you'll do, fractional oxidation states are possible. For example, iron in the compound iron 3, oxygen 4, or Fe3O4. Each oxygen in the compound has an oxidation state of -2, leaving each iron with an average oxidation state of 8/3. Very common example of redox reaction is rusting, where molecular oxygen is reduced to form hydroxide ions. When the final equation is separated, again, there are half reactions as seen before. Combining the two half reactions after multiplying the first so that the charges are balanced gives this equation. And the precipitate of iron 2 hydroxide formed is rapidly oxidized under basic conditions to form essentially rust. When balancing redox reactions, there are three conditions in which they can be balanced. If the reaction is occurring in a neutral condition, acidic condition, or an alkaline condition. The conditions are as follows. Examples will be given. For neutral conditions, half reactions must be separated and the electrons must be equalized, meaning that you multiply one of the half reactions on both sides in order to get the same amount of electrons, or both half reactions in order to get the same amount of electrons. The equations should then be added together and the charges should be balanced at this point. Here's an example. When balancing the equation copper +1 and iron, and the other side is iron +3 and copper, you would separate the equation into its half reactions, where copper has been turned to +0 essentially, so you need to add an electron on the plus side. Same with iron, you would need to add 3 electrons on the iron +3 side. Then you would multiply the copper reaction by 3 on both sides in order to match the number of electrons on both sides. Then you would add the two equations together and get rid of all the common terms. And that's the balanced redox reaction. In acidic conditions, the half equations must first be separated. Then each half equation should be balanced except for oxygen and hydrogen. Next, add water to balance oxygen. Next, balance hydrogen by adding H+ protons. The electrons should be equalized, and the equations should then be added together and the charges should be balanced on both sides. Here's an example. balance the equation Cr2O7 2- plus HNO2, and it turns to Cr3 plus NO3 . So first you would split the equation into its half reactions. As you can see here, you disregard the hydrogen and oxygen essentially. So you would split Cr into one half reaction and N into other half reaction. Then you would balance the half reactions so that the number of non-hydrogen and non-oxygen atoms on both sides are the same. In this case, you'd only have to multiply the second part of the first equation by 2. Next, you would add H2O in order to balance the number of oxygen on both sides. In this case, there are 7 oxygen here, so you multiply by 7 H2O in order to match the number of oxygen. In this case, it's O2, so there's and O3 over here, so you're missing 1 oxygen on this side, so you would add 1 H2O on this side. Step 4, you add a number of H plus protons in order to balance the number of hydrogen added by the water essentially. And you would balance the number of H plus hydrogen on both sides. So add 14 here because there's no other hydrogen apart from the hydrogen from the water, and there's 14 there. In this case, there's 1 here and there's 2 here, so you add 3 H plus. Next, you add a number of electrons so that the number of electrons is equal on both sides. So counting the charge, you get plus 3 here and another plus 3 here. So this side has a total of plus 6, and this side has plus 14 minus 2. So that's plus 12. So you want to have plus 6 on both sides, you need to subtract 6 from the left side. You have plus 6 charge on both sides. Same idea with the second half reaction, except you only need to add 2 electrons on the right side. Now you equalize the electrons, meaning you multiply the second half reaction by 3, and you get 6 electrons here. Then you add the 2 half reactions together to form this equation. In alkaline conditions, the half reactions must first be separated, balancing for hydrogen and oxygen as seen before, using water and H plus protons. Then you equalize the electrons in the same manner, and you add together and the charges should now be balanced. The difference from acidic conditions is that next for each H plus proton, you add an OH minus ion on both sides. Finally, combine the H plus and OH ions to form as many water molecules as possible and remove common terms from both sides. So in this case, Ag plus Zn2 plus turns to Ag2O plus Zn. And first you would separate into half reactions, and you would balance the non-hydrogen and non-oxygen elements. So you multiply this by 2. Then you add H2O in order to balance the oxygen on both sides. Here there's only 1 oxygen atom, so you only add 1 H2O molecule. Next, you add an equal number of H plus protons as seen before as in the equation to balance the number of hydrogens. Next, you add a number of electrons in order to balance the charges on both sides. Here you can see this charge is 0, and this is plus 2 without the electrons. So you need to have 2 electrons in order to balance the charges. In this case, this is plus 2, and you have to have minus 2 in order to balance the equations. Next, you add the 2 equations together, and you can, at this point, essentially remove the electrons from both sides, and you get this. Next, you would add a number of OH minus molecules to compensate for the H plus protons, essentially. Since there's only 2, at most, H plus protons on one side, you would add 2 OH minus molecules on both sides. At this point, you would combine it so that you would get water, over here, as seen, the H plus and OH minus combined to have water, and there's no H plus on this side, so OH minus remains the same. Then you remove the common terms. For example, this H2O, and there's two H2O here, so you remove one H2O molecule from both sides. And this is the final reaction.